Okay, so let's get started. So let's quickly recall what we last time what we did. So it is 4:23. So class will be off at 5:20. So last time we discussed how we can define variables in MATLAB. So there is x equal to 1. So x is the name of the variable and 1 is the value assigned to the variable. And x, this is also another variable which is totally different from x. And we have assigned a value 1 to it also. And capital X represents another variable which is different from other two. And it is also a valid variable name. So then we also defined x1, which is also a variable name. So x1 is a valid variable name and we assign it a value of 10. So then we also like try to name a variable like 1x, but we saw that there was error. So this is not a valid MATLAB variable name. So we cannot write 1x. So the rule is that MATLAB, while naming a variable in MATLAB, you cannot name it starting with a numeric value. So you can use numeric, but it should be on the other. It can be in the middle or it can be on the right hand side. Not, it cannot be on starting of the name. Similarly, then we defined like x equal to 5 was first variable, y equal to 3 was second variable, and then we defined third variable x, which which was equal to the sum of these two variables, that is x plus y. So, and similarly, we defined x minus y, and then we defined something as the multiplication x star this y, and we can also define division, that is x by y. So all these are new variables. S is new variable, SB is new variable, D is new variable, M is new variable. So all of these are the variables. So, and then we defined something like this, creating array of numbers. So let us continue with this. I will let us create a array like this: 1, 2, 3. So I am giving space between the two elements, and you can see it will create. So it is creating a row vector, and you can see in workspace this variable has assigned this array of numbers. Okay, so pressing up key in the, so I am pressing up key and you can see we can navigate through this. So let me amend this and I will put semicolon here, and 4, 5 and 6. So now you will see that another row has been created. So basically this column, when we add colon, so we can create another row. So 1, 2, 3 is in the first row, 4, 5, 6 is in the second row. So now the question is how we can access to these elements. For example, we want this one. We know that x is storing a matrix 1, 2, 3 in the first and 4, 5, 6 in the second. So let's assume we want this 6. How we can get this 6? So let's type x traces. So we can see it is in the second row and third column. So I will type 2 comma 3. So you can see 6 has been popped up. So basically we can have an access to each of the elements of this matrix. How we can access? We have to just type x and we have to write the indices. We have to write what is the row number, what is the column number, and put a comma. We cannot give space here. We have to write comma in between the elements. So we can see that x2 comma 3 represent a 6. Similarly, you can see if you type x of 2 comma 2, you will get 5, and so on. So let us now, if we want this whole row, We want 1, 2, and 3. How we can access? So I can type x of 1, that is first row. I need whole row. So one thing is that you can type x comma 1 1, then you can type x comma 1 2, then you can type x comma 1 3. In this way you can access, you can get all the first row elements. But we can also type 1, that is first row comma this colon. So when you write this x1 comma colon, you will get the first row. So you can see 1, 2, and 3. We get the whole first row. So similarly, if you want, for example, this column, second column, you want second column, how you will get second column. So x, now I will write column first, that is it will give me uh comma 2. So column means that it is in the second column and all the rows. That is second column, first row, that is 2. That is second column, second row, that is 5. So all the elements in the second row we can get by writing this. So you can see 2 comma 5. So in this way we can have access to different values of the matrices. So also we can store these things. So this is also an array. This is the row vector, and it has been stored in ANS by default because we don't have used any variable to store these things. We could have, like I can write uh, first first row equal to, I can write first row equal to, what was first row? This. I'll just copy this and paste it here. So now you can see that first row, which is given by x of 1 comma colon, that will get stored in first row. So you can see here, first in workspace, first row stores 1, 2, and 3. Similarly, you can store the column and other things, and they will get, the variables will get introduced in this workspace. Okay, so one more thing. Yes, so we can also like type a equal to 1 1 10. See what the result comes. So you can see when you type 1 colon 1 colon 10, you get first element as 1, then it is adding 1 getting 2, and adding 1 getting 3 1 1, and you can see it runs till 10. So this number represents the final number you want. This middle number represents the addition. Okay, and this number represents the first element. uh you can also write, we can write b equal to 1, no, let us take 3, let us take 1 and add 3, and we want it to be, let us suppose, up to 12. So you can see we have got 1, 4, 7, and 10. So we cannot get 12 because it is not possible that while adding 3, when you add 3, we get 4, we add 3 more, we get 7, then we again add 3, we get 10. If we again add 3, we will get 13, which is beyond this. So actually, these are putting the limits. To be more specific, this is putting the limit. Okay, with these things, I think it is so. While we are doing the algorithms, new commands and new things will come, and yeah, yeah. Go ahead.
B is equal to 1 colon 3 colon 12. So it is not clear, sir.
Okay, so which one?
B is equal to 1, 3, and 12.
Okay, 1, 3, and 12 is not clear. What is not clear? First element is 1. Is it okay?
Yes.
Then we will add 3. 3 plus 1 is 4. Is it clear? Again, it will add 3. We will get 7. Again, it will add 3. We will get 10. Again, it will try to add 3, but when it adds 3, it will get 13, which is beyond this 12. So it
Okay.
cannot, we cannot get to 13. Okay. So किसी और को कुछ क्वेश्चन है इस रिलेटेड या मैं आगे चलूं? एनीवन?
इस सर वो फंक्शन आता है ना सर, वो लेंस स्पेस, इसमें और उसमें क्या फर्क आती है?
हाँ, we will get. So okay, let's do it here. Yeah, let's take. So lens space, let us take 1 comma 10. Okay. So now you see what is the difference. Are you getting or not? So we have got 1, 1.05, 1.18, 1.27. We have got all the numbers up to 10. So basically it has created random numbers from where it has. We have used lens space 1 comma 10 and it has created large number of values which are ranging between 1 and 10. Okay, you can also tell, okay, let us take another thing. Let us use lens space, okay, and type 1 comma 1 comma 10. Okay, so now you can see what has happened. So you have now 1, you have created 10 times this number, that is 1. Okay, so let us use lin space 1. So what will happen? Any guess? Yeah. Any guess from anyone? What should happen? Hello? Are you there? Okay, no guess. So let us hit enter and we will see what it is. So
Yeah.
now you can see we have got only 10 and we have got it only once. Okay, we will get to this function more when we will be using in today's lecture. Like we have to simulate a particle which is moving in a straight line motion. Okay. So in today's lecture, we will be simulating a particle which is moving in a straight line. So let us first see what I mean by this. So this is a particle which is moving along a straight line. Am I audible?
Yes, sir.
Yes sir.
Okay, so this is a particle. This is a particle where there is cursor. So initially it is resting here. So it is position vector is r naught when it is at this position at t equal to 0, and then it starts moving in a straight line. So at any instant of time t, its position is given by this vector r, and its x coordinate is x of t comma y of t. Okay, so since its velocity is constant, I can write its velocity equal to some constant times v hat, where v hat is the direction along this velocity direction. And this v hat is unit vector. It is not a varying vector, it is a constant vector. By unit vector, we don't mean that it is a constant vector. Remember, there is a difference between a constant vector and a unit vector. Unit vector has just magnitude constant. It need not have a constant direction. So you can imagine a vector which is moving in a circular fashion, that a unit vector. So constantly it is varying its direction, but its magnitude is 1. But here I am saying that this unit vector is not changing its direction. it is a constant vector like this I vector. This is a unit vector along x direction. So it is a constant direction, always pointing in this direction. J is a unit vector which is pointing always in this direction. So these are fixed uh, unit vector. Similarly, I have defined a unit vector v hat which is pointing in this direction, the direction in which the particle is moving. So since this is a constant, I can write this unit vector as cos of theta I plus sine of theta j. Oh, I think I have used some rough here. If it is there, I can show you. Okay. Oh no. Okay, let us do some. Okay, so I am saying that this is I cap and this is j cap, and let us see that this is our v hat, that is the unit vector along. So this, since this is in a it is pointing in a constant direction, so there will be a theta which it makes with the x-axis or the I cap. Now I can write this unit vector. Every vector I can write as its x component, which is nothing. It is magnitude is 1. Okay, so it is magnitude is 1. So it is x component will be 1 cos of theta, 1 cos of theta, and that will be directed in the x direction, plus it is y component, that is this, it will be equal to 1 sine of theta, and this will be pointing in that. So we can write this v vector as cos of theta I plus sine of theta j. Okay, is it clear?
Yes, sir.
Okay, so getting back, so now you can see that this unit vector is cos of theta I plus sine of theta j. Now we can write this v vector, which is nothing but c times v. So c times this v, c cos of theta I plus c sine of theta j. C cos of theta, theta is constant, cos of theta is constant, c times cos of theta will be constant. I have represented that new constant by c1. Similarly, constant times constant will be another constant. I have written down that as c2. Okay, now v is also equal to d by dt of rt. You know, the differentiation of the position vector gives us the instantaneous value of the velocity. So this is the instantaneous value of the velocity, and it is given by d by dt of rt. Is it okay? Any question till now? Yeah.
No.
Any confusion?
No, sir.
Okay. Okay. So V is d by dt of R of t. So d by dt of R position vector can be represented as xi plus yj. If you remember from first lecture, we can represent a position vector R as xi plus yj because its x component is x and its y component is y. So I can replace this R by xi plus yj. So d by dt of x times I, because I is constant, its differentiation will be 0. So dx upon dt I plus y dy by dt j. So this is the velocity. Now you can see, okay, we define this dx upon dt, that is rate of change of x coordinate of the particle. So when this moves, this particle moves along this thing. So you can continuously track its x coordinate, that is also changing. So what is the rate of that change? We denote that by u, that is dx upon dt is u and dy upon dt is v. So x component of the velocity, v component, that is y component of the velocity is denoted by v. Okay. So from first and second, so this is the first where you have written v equal to c1 I plus C2j, and then there is V equal to Ui plus Vj. So comparing these two, we can see that U is equal to C1 and V is equal to C2. So U is equal to C1 and V is equal to C2. That means if a particle is moving in a straight line, its x component is constant and its y component of velocity is also constant. I could have directly said this, but you may have questioned that how you can write that its x component is constant. So this is the way we can show it. Okay. So now I will write this dx upon dt as x dot. That is the rate. Whenever there is change with respect to rate of change with respect to the time, we usually denote it by dot. So x dot equal to c1. Nothing. I have written this dx upon dt as x dot equal to c1. Dy by dt as y dot equal to c2. Okay. So rate of change of this x is constant. Rate of y is also constant, but these two constants may be different or they may be same. We will see what is the difference if they are same or they are different. Okay, so then we define, let us define z equal to x y. So z is a matrix, or we can say it is a column vector where its first input is nothing but the x component of the particle and its second component is nothing but the y component of the particle. So differentiating this, we can get z dot with respect to time, obviously. We can get z dot equal to x dot y dot. So now you can see what is our intention. So our intention is that a particle is moving on a straight line path and we want to simulate it. By simulation, what we mean? We mean that we should know it at any time. We should know its coordinate. What is its x coordinate? And what is its y coordinate? If we know what is its x coordinate, if we know what is its y coordinate, we will plot x comma y and that will pop up here. And with the varying time, that point will also vary and we can see a point moving. Okay, so this is the purpose of this class. So let us now go to the MATLAB and see how we can do these things. But before shifting to the MATLAB, so let's first focus on this thing. So we know x dot and y dot. If we know x dot and y dot, can we get x and y? Obviously, yes. So let's shift to blackboard, whiteboard, sorry. So if we know x dot is equal to nothing but dx upon dt, which means dx is equal to x dot dt, or x is equal to integral of x dot dt. Similarly, y is nothing but integral of y dot dt. In the similar fashion, you can see that if we have zeta dot, we can get z, which is nothing but x, y, and which is nothing but integral of what? Integral of x dot y dot dt, and which is nothing but integral of x dot y dot is z dot dt. So you can see actually we need this xy, which is nothing but this z, and we know x dot y dot, which is actually zeta dot. So basically, if we know the zeta dot, we can find the z. Okay. Okay. Also see that we actually want x. Yeah. Anybody having any question?
We have a initial condition option on that integral part.
Okay. We will see the once I will shift to the MATLAB. We will see if we need initial condition or not. Obviously, there will be, but wait till we reach there. Okay. Is it fine?
Sure, sir.
Okay. So I was saying that our z is nothing but x, y, and what we, and this z is a matrix storing x and y, but we need x. So just a few minutes before we saw that if we have a matrix x and y, we need this element, and this element is nothing but z of 1. Similarly, y is nothing but z of 2. So keeping these things in mind, now we will try to see how we can simulate this thing. Okay. So I have already written a program for you, uh, which you can practice at your places also. So let us see. So this is how you should make a habit of writing a program. First, it should be your name, and then it should, uh, and then there should be the date on which you are creating it. And here I have written what is the course name and where this course is being uh, offered. So, and then this is the name of this program, what we are going to do in the program, particle moving in a straight line. So when we add this percentage, we are actually commenting this. So this is basic. This is not the part of the program. Remember, whenever we use this percentage type, it just makes the things comment. So these are just commenters there. Okay, these are not the part of the algorithm. So starting with close all, CLC, and also C, I can write these things at this. Okay, so close all means if there is any figure which is open, that will get closed. CLC means if there is anything in the command window, it will get cleared. And clear all means if there is any variable which is there in the workspace, that will get clear. So I can show you when I will write CLC, you will see that anything written here that will get cleared. So you can see, but this doesn't this has not got cleared. Okay, so now I will write clear all, clear all. So now you can see, I if I hit this, you will see there this will get cleared. So you can now see it has been. So why we are doing this, you will get to know when you will start programming yourself. Okay, and I will also tell you, but this is not the right time to tell these things because you should get some feel of these things. Okay, so first is the simulation duration and speed. So some things will be there which I will not explain at this time, but you just bear with me for some lectures till we get the right time to explain those things. So T end, this is the time up to which you want your particle, or it is the time up to which your particle is moving. Okay, so you want to simulate for 10 seconds. So this is that time. And this T end, this is just a variable name. Okay, so I named it as T end. I am storing this 10 in that variable. And then there is animation speed, which you don't need to understand at this time. And then there is T span, which is showing us what is the start time and what is the end time. So start time is nothing but it is a 0 obviously, and the end time is this 10. Okay, so this is the T span. We will be using it somewhere, I will show you. So now is the initial condition. Someone correctly pointed out, is there any initial condition? Yeah, there is initial condition, because when you are integrating, you need some initial condition. So initial condition will be on X and initial condition will be on Y. So where your particle starts. So this, if for example, if it starts from here at t is equal to 0, it is at origin. So your initial condition will be 0 comma 0, which I have shown here. Okay, x dot y dot. So I have already told you that x dot and y dot are constant. In our case, x dot and y dot are constants. So I have used x dot and y dot as constant, 0 0.1, 0 0.1. Okay. Then I have defined z dot as nothing but x dot colon y dot. Can anybody tell me, is this a row vector or this is a column vector? Yeah, this z dot equal to x dot colon
Column
y.
vector.
It is a column vector. So its first element represents.
So the first x derivative.
Okay, so it represents x derivative. direction x component of the velocity, and its second denotes y dot, that is the y component of the velocity. Okay. So then what I am doing, I am writing c z dot. Uh, okay, let us go back to this. So you can see I am trying to integrate z dot. I am not trying to integrate x and y individually. I am trying to integrate this z. Okay. So our initial conditions should also be in some form as compact form like in z. So that is why I have written z naught. I am defined. This is another variable. Z naught is another variable. And I am saying that this is the initial condition. So what is the initial condition? Initial condition is x naught. Okay, so z naught is nothing, but it is z is the x and y component of the particle. So z naught means the initial position of the particle. I am writing it in the vector form. I am not writing it in the component wise form. So z represents the x component and y component simultaneously. Okay. Uh, then you can see now we have x dot y dot and we have initial conditions. Now only thing is that now we should be able to integrate this thing. Okay. So for that I have used a function. This is a function. So you might not be knowing this thing. So let us go back and see here what this is. Okay. So let us define uh, at x square plus y square. Okay. So I have defined, and I will call this function as, so who is in the class, I will see. So Dayan. Okay. So let me first see what. So so others have left it, I think, huh?
Yes, sir.
Okay. Okay. So x square plus y square. So I will define this function as Dayan. Okay. Uh, Dayan equal to at x square plus y square. Okay. So now we have a function Dayan, and this function Dayan, if we give it will have two inputs. One is x and another is y. And once we give these two inputs to this function, we will see that it will give us it will return as the scare. It will scare these two things and then it will add these two things. Okay. So let us see what we will get. Oh, something is there.
Sir, the
Okay.
dot or
Yeah.
the dot is missing.
Dot is missing, but dot is not important. Something is missing. Okay, let me go to this thing. Okay, I have not mentioned. Okay, so I have not mentioned. Uh, so you can see here, I have not mentioned what are the variables. Okay, so variables should be x, comma, y. This is what we were missing. Okay. So x and y are the variables. See, these are not the variables. You can put large number of things here. Among those, what are the variables this function will consider? That you have to write here. So x and y are the variables for this function. Okay. So now when I enter, now Dayan function has been created, and you can see here, yeah. So uh, and this Dayan function has two variables x and y. So I will write Dayan, and I will give x, that is 1, and y equal to 2. So what should be the answer to this function?
5.
So 1 square plus 2 square, that is 5. So
5.
5 should be the answer. So you can see 5 is the answer. So this is how we create functions and how they take the value. Okay. So now let us go back to this. Okay. So I have created a function. I have created a function. Okay. I have created a function which is nothing but a function of t and function of z. Okay. What is that function? It is function of time and it is function of z, which is whatever we have as a variable and we want to calculate. Actually, we want to calculate z, and this function is nothing but z dot. Okay. So this function is nothing but z dot. What we want to integrate this function, what we want to integrate this z dot, it takes that. See, this z dot is equal to our RHS function. So this RHS function will take t and z as the input, and it will calculate as z dot. It will give us the value of z dot. Okay. So what are the inputs? Inputs are time and inputs are z values, and it will return us z dot. But you can see from above, the z dot is x dot y dot, and x dot and y dot are constants. So for this special case, this function is a constant function. But this will not be the case in this will not be a general case. Okay, so this is a particular case from where we will be starting. Okay, so if you understood this, then we have something small and option. I will not tell these things. These are something which are related to control the errors. I will explain these things, but at this moment of time I want you to focus on uh, something else. Okay, so I have already told you there are some things which you have to bear with me for few classes. Okay, any doubt?
Sir, should we try to write our own derivative solvers or integration solvers, those simpler ones like the
Yeah,
Euler?
yeah, that is better. I was like thinking that I will tell you that we should create our own this thing. Yeah. So it is
Yes.
better if we create our own ones, like we can use Rungakuta method, and also you can see these are also using the same. So that is better. Like if you see, I have also created my own, but now why I am using this one? Because this has so much it is very it has got very advanced now. You can see abstol and reltol. It will give a very close tolerances of the error. Okay, that is all the only reason. But yeah, it is encouraging if you develop your own solver. If I get the time, I will in some lecture I will try to explain, and maybe we will just create our own solver so that you don't feel that this is something which is ready made. Okay, so at this time you will feel that we are using something which is already there in the library, but we can create our own ones. Okay, so it is just that we should get some time. You already see that the time is very limited. So basically I want you to get familiar with how we are creating these animations. Okay, so that is the only reason. Okay. Okay, so I am here using ODE45. ODE45 solver will integrate my z dot. So I have this z dot, which depends upon time, and which also depends upon what is the value of z. And using those things, this RHS will store the value of z dot. Okay, what is the value of z dot? Once we get the value of z dot, this solver now takes the value of z dot as input. It also takes the time span for which you want to integrate it as the input. And it also takes the z naught, that is the initial value of z as input. And this option is nothing but this thing, which I already told you that it controls your error. Okay, abstol and reltol. I have entered this small value, that is e raised to power minus 12. and it will control the error value. You will see, if we try to relax this constant, you will see how our solution will deviate from normal. Okay, you will see these things. So once we do this, ODE45 will now integrate the things, okay, and will return a solution, and I am storing that solution in a variable known as solution. Okay, this solution will store that thing. So now I am using here t equal to linspace. I think you questioned what is the reference. So here I am using linspace 0 t end. So 0 is my starting value of time. T end is my final value of time, and I am slicing it into the 1,000 steps. Okay, so I will get 0, and then I will add 1 by 10,000 step, and then again. Okay, you can see it from. Okay, let us run it. Okay, at final I will tell you these things. So we will get 1,000 values of time here, and then I am using something. See, you can also see on YouTube or maybe some other things. You will see that they are just storing it here and then using directly. But I am using it in a different way. There is a reason for this. So I am using deval. Deval is an inbuilt function in MATLAB. What it tries to do, see, this OD45, it has integrated already integrated your solution. Okay, so now what we are trying to do, you have got the area of x and y. Now we want this x and y at some time t. Okay, so this deval will take that whole solution and will return you the value of z, that is x comma y, at some time t. Okay, this is where you want this solution. Any confusion? I think this part will be tough for you at this time, but you have to, like, you will get used to this thing. But to some extent, have
So
you got? Yeah.
in lens space, we don't need to worry about with what increment we have to increase. We just
Yeah,
need to
yeah,
tell him
yeah, yeah, yeah. It will
which
equally space.
piece is.
It will, yeah, it will equally space this 0 to t. And for example, what we have, 10. Okay, so it will take 0 and it will take 10, and it will divide this interval into the 1,000, and then it will give first plus that increment give second, plus that increment give third, and it will give 1,000 times steps between 0 and 10.
Sir, is
Okay.
this Z deval creating a 2D array of X and its corresponding time, or it's
What?
still a 1D?
Okay, okay. Z, you are saying?
So I'm
Hello?
saying, sir, is that deval function taking the solution and creating a sort of a 2D array of X with its T element and Y with its T element, so
Oh,
that whenever we plot at some
I'm,
time in.
yeah, yeah. Yeah, yeah. But what is our T? Our T is not a time instant here. It is 1,000 times steps, isn't it? So
Yes, sir.
at each time, this deval will give us a solution. See here, when OD is running, it is not like, it is not giving you the value at, for example, 0, and then it will take some time step and give you the value. No, it has its own algorithm running behind, and it will create values at some instant and will leave at some instant. But you want the solution at some given instant of the time, so you create your own instance of time. And then devolve, what devolve does, that it takes that solution and see what is the solution at your instant of time steps. Okay, so this
So it is
z,
creating
it will,
it's,
yeah, it is creating. So this z will store, uh, a, a list, 1,000 number of values in the first row, 1,000 number of values in the second row. Okay, so this will be
Okay,
a 2 cross 1000 array. Yeah.
so the solution matrix has intermediates as well, like which we don't
Yeah.
need.
Yeah. That is what I am saying.
Okay, sir. Thank you, sir.
Okay. So now, okay, let us run if I am able to run it till this so that we can see. I hope I can. I have put a stopper here. Okay, let us run. So now we can see what. So yeah. So you can see T. T is nothing but 1 cross 1000. If we open this, so you can see we have got 0 time and then 0.01 time, 0.02 time, 0.03 time. So there are 1000 steps between 0 and 10. Finally, we get the 10 second. Okay. So it has divided time into 1000 seconds. Okay, let's close this. Similarly, you can see Z. So you were saying about Z.
Sir,
So
what
you
if
can see Z.
have
Yeah,
that T,
yeah.
if the solution has created a value for some T and
Yeah,
the interval doesn't have that, like we have created for 0.001, what if the
yeah.
doesn't have that intermediate for 0.001? What will happen in that?
Yeah. What it actually does is it connects the 2 point and calculates the average at that point. So it will have some value behind it, and it will have some value in front of it. Okay. So what this deval does, it creates an average value of these two. Is it okay?
Okay, sir. So for everything within that interval, it puts it out either the lower one or the higher one.
It creates average, something like this.
Okay, sir.
Average. If it is exactly where it is calculated, that it will take that value. Okay.
I will use the
Or if it is in between, it will create the average. But these are not too much different because the interval is already very small. And if you increase the interval, then you will see how your solution and your animation will be distorted. You will see those things.
Thank you, sir.
Okay. So where am I? Okay. So you can see now this Z, it has two rows of numbers, first row and second row. So first row lists the value of X coordinate. Since we have 1000 time instance at 0 instant of time, what is the X? I will show it again. So this represents the X coordinate at t equal to 0. This represents the X coordinate at t is equal to t1. At this represents at t equal to t2. That is second time step. Third time. What is the X value? These are the what are the Y values. So now we have basically and this whole is Z. This whole is Z, and its first row represents the X coordinate. Its second row represents the Y coordinate. Okay. What we need X and Y. Now I have to extract the first row. So I think 10 or 20 minutes before we saw that if we have this matrix, how we can extract its row. So Z is a matrix and we want its first row. So Z of 1 comma colon, this will give us the first row. Similarly, this will give us the second row, and second row is nothing by Y but Y, and first is X. Okay. So once we get this, this is what we need. So we have got X and Y. Now we only need to plot this thing. Any question till now? Yeah, Mustafa, I think you are silent. Anything wrong?
No, sir.
Have
Actually,
you?
this is, sir, this is new for me, so I am just listening carefully.
So I
And
am this is lecture. This course is also for those who are new to the MATLAB. This is not for those who are very well trained with the. So I am. You are supposed to ask questions and confusions. If you are not able to follow, you have to stop me. That you are going too fast. I am not able to catch up you. So you have to tell me. You have to don't think like that others know. That is not the purpose. Okay. So if you have any confusion, or you are not able to get something, it is not your fault. Okay.
Sir,
So just stop
is
me at there and tell me where you have not understood. Yeah. So कहाँ तक आप जो है ट्रैक में रहे और किस कहाँ से आपको लगा कि यहाँ से तो कुछ समझ में नहीं आ रहा है? हम्म। हाँ मुस्तफा आपसे मैं बता रहा हूँ।
ठीक ठीक है, मतलब सर मैं समझ रहा हूँ सर, क्या क्या मतलब क्या क्या हो रहा है,
अच्छा अच्छा ठीक है तो then it is
समझ रहा हूँ सर
just a matter of practice. Okay.
किस तरह है। हाँ वही है सर।
Okay. Even there will be recording and other things. I will send it to you. And when you go back, you revise this thing. And if you are not able to get something, you can contact me. Okay. This is for everyone. Okay. Let's continue. Uh, so now we have got all the values of x at different instances of time and all the values of y at different instance. Now only thing is we need to plot this thing. And there is a difference between animation and plotting. So you can plot this x and y. You have x-axis and you have y-axis. You will plot these two along each other. You will get a static line that will not be a dynamic. But in animation, what we try to do is that with the passage of the time, we want the things to be dynamic in nature. That it should it should show us how the things are changing with the time. So that is the purpose from now. So this is the animation part. We have a clock in the MATLAB. So I start this clock. Once I press this stopwatch, that's tick. Tick means that I am pressing the clock. Okay, I write tick. So when this algorithm start running, and when it will reach this tick, imagine in your head that we have pressed a stopwatch. So stopwatch has started. Okay, so I am initiating a variable time and setting it to 0, and I am using hold on. Hold on will do that any figure, any number of figure or any number of plots, they will come on the same figure, one on top of other. Okay. So it is not like that if I am plotting this and then I am plotting this, first this will be created and then this will be created. No, this will be created and this will also be created on that figure. That is what this hold on does. Okay. After this, now what I have to plot? I have to plot, uh, okay, before going to animation, let us run this thing because I want to show you something. So I am uncommenting this. Okay. So let's run. So you can see, oh, okay, this whole has run. This whole program has run. That is why whole trajectory was there. Okay, let's stop here and run it again. See, you can see that particle has started from 0 comma 0, which was our initial, and it is moving in a straight line path. But this is not showing that the particle is moving. This is just that you have taken x values and you have taken y values and you have plotted a graph between x and y. This is that much and nothing else. Okay. So this is what I mean by plotting these x and y. Now what is animating, that I will show here. So I have started a watch by tick, and then I have initiated this new time variable t hyphen uh, and I have initiated equal to 0, and then I am using hold on. Now see, I have to plot the particle. So where the particle is initially, it is initially at x0 and y0. So I am using plot command, and in plot command I am using x0 y0. That is, I am plotting x0 and y0. So this will plot a point. Where it will plot a point? At x0 y0 coordinate. And I am then using this dot, so this x x0 y0 will be plotted as a dot, and its color will be black. So k stands for black. So don't forget to enclose these things in these commas. These are uh, otherwise it will show you the syntax error. Similarly, then I am using marker size. So what will be the size of this point? I have taken it as 50. You will see how much big it is. Okay, so through this, I am using, I can create a dot at x0, y0 coordinate. Similarly, this will just plot a particle. Now, if, okay, let us consider this much. Then it will plot the particle at x0, y0. But we know that as the time passes, that particle doesn't remain at x0, y0. It will keep on moving. Okay, so how my plot will keep plotting this dot at different different points at different instants of time. For that, I have not used plot x0, y0. I have used particle equal to plot. So here I am creating a handle. So by creating a handle, I mean मैंने एक handle create किया है जिसको मैं घुमा सकता हूँ. Okay, so that is why it has been known as the handle. So particle will be acting as the handle for this plot. Okay, now see, this much I am not showing at this time to you particle trajectory. Okay, I will shift to this while. So see, I am saying that while t, that is this time, while t is less than t end, because I want to run this simulation for only that amount of time, and for that amount of time I have a solution. Beyond that time I don't have a solution, so I cannot run it beyond that. I cannot animate it beyond t end. Okay, now see where this deval helps you. Z equal to deval solution t. We have a solution which is storing the values which we have got from the integration. But I need that solution on this instant of time. This is the instant of time. This is not the span of time. This is just an instant of time. At this instant of time, what is the solution? Deval will just make it sure that we have available it at this instant of time. So z equal to deval solution t. This will give me the x and y values at this instant of time. Okay. So once I get those two values, that will be stored in matrix Z as one first element in the first row and second element in the second row. But I want x and y separately. So I write x equal to z of 1, y equal to z of 2. Okay, so these are the only two elements present there. Z of 1 will be the x coordinate, z of 2 will be the y coordinate. Now, in my plot, I want these things to be plotted, x and y. What are the current values for x and y? I want these to be plotted. So I will write particle dot x data. This will update my this thing, x coordinate of this plot. Its handle is, sorry, its handle is particle. So I have used particle dot x data. This means that I am updating its x coordinate. And what is the new x coordinate? This x value. What is the y coordinate? This y value. Okay. So I have updated my x and y coordinates. I will not show this thing. I am again saying this. I will show it in the next class because it will become too much for you. So once I get the updated value for x and y, now I tell my MATLAB to draw it now. So this is the command draw now. It is not necessary, but if you do it, it will immediately draw it. Okay, so T now, draw now, and this is something it has to do with the animation speed. I will not cover it at this time.
So
We can commit it.
frame control thing.
Yeah, yeah.
Is that frame rate control thing? Like when you control for various
Yeah,
frame.
yeah. This is related to that, but that is what I am saying. I will not tell this thing at this time. It is not important at this time. What I just want is that whatever I am saying, that you are getting it in a good way. Okay. So because of the constant and the time, that is the only reason. Otherwise, I have put it there to show you. Okay, so let us go now and see how it works. So you can see a particle has started from 0 and it is moving and it has moved whatever it needs. Okay, so it has moved for 10 seconds, I suppose. Okay, 10 seconds. Okay, so its animation speed was 1.2. That is why it doesn't move for 10 seconds. Let us take it one and see. So you can start your stopwatch and you will see it will run for 10 seconds. Okay. So I think 10 seconds are that much amount of time. If my program is working good, which I hope it does. Okay. Let us change our initial condition. Let us take 1 comma 0. So it will start now at coordinate 1 comma 0. Okay. We are not changing this x coordinate of the speed, y coordinate of the speed. We have just changed the initial condition from where the particle has started. Okay, let's see what happens. Okay. Okay, you can see now it is starting from 1 comma 0. It has not started from 0 comma 0. Okay, it will again run for the 10 seconds. Okay, so okay, so let us now change the speed. Let us put it 1 and 1, which is very large speed. You cannot imagine. Yeah, you can imagine, but you cannot appreciate that this is large. It's large speed. It is a constant speed, huh? Okay. So let us do one more thing. You can play with these kind of, see, I want you to play with these programs and animations, because the whole purpose is not to just write the algorithm. You have to understood something from these. You have to also understood the physics. So the basic purpose of this course is you write your algorithms, you animate them so that you can visualize the things. So if you have created your algorithm but then you are not playing with it, so then there is no purpose of creating the animation. Okay, so you have to play with you have to change initial conditions, you have to change speed. Okay, let us do one more thing. Let us take this 0.1 and 0.1. Let us do, I have already told that this z dot is constant. Obviously this is constant. This z dot is nothing but 0.1, 0.1. Now let us put here t square. So now this is a function of time. You are seeing now this function, which is actually z dot, RHS storing z dot. I have created that as a function of time. So now you can see. So can you guess what will happen?
Maybe sir, it will sir trace a um, curve path, sir.
Yeah,
Parabola path.
but I have already told you that it is a straight line motion, isn't it? Dayan,
Yes, sir.
can you guess what will happen?
Can you repeat again? Just I got it right.
Okay, so I am saying that before here there was no t square. Okay, it was z dot only. So we had constant z dot, and we were getting a constant speed. So now I have introduced a t square here. So now my RHS, which will be integrated by ODE, that has a term t square. So can you guess what will happen to our animation? How it will change?
So now our velocity, that velocity derivative is not constant, so we have an acceleration there.
Okay,
So because
so Yeah,
a
yeah.
parabola,
So
at least.
according to you, it will be parabola. So both of you are saying that we will be getting parabola. Okay, let's see.
Sorry, it's multiplying on both elements, so it will still be a straight line, but
Okay.
it increase speed because
Yeah, yeah. You have got right. You have answered it right. So basically, what you are doing, you are multiplying this t square outside, okay, and it is canceling on when if you take u up v upon u, it is canceling on numerator and denominator. So you are getting a constant heading of your velocity. Okay, so that is the reason. So, but your acceleration, your x component and y component are continuously increasing, and they are increasing proportionally so that the direction of the velocity doesn't change, but the magnitude of the velocity changes, and that is reflected in the animation. You saw that how the particle started with a lower speed and then it increased it as t square because the time was increasing, the velocity was also increasing. Is it clear?
yes, sir.
Yeah.
Yes, yes, yes.
Okay, so I want you to play with this. I am so it. I will also send the send this video. Maybe I will upload it first, and then I will send link to you. Okay, so you play with this thing and try to get and try to swallow because I have a different way of writing my program. Okay, so you have to understood that I am using vectors and I am not using the scalar components like x and y. And there is an advantage. Once you get used to this thing, you will see how the things are getting very compact. Okay, so you have to make sure that you feel comfortable with each passing day with this vector form. Okay, so I am using z as x, y, and so on. If we go to the 3D, I will be using x, y, and z. Okay, and also uh, okay, I have nothing to say, I think, for this class because already we have exceeded 10 minutes. If there is any question or any confusion you have, you can tell me. Otherwise, we can call it a day.
Sir, where will you post these? Or is there a GitHub or in the group?
Okay, let me first do one thing. Okay, just wait a minute. Uh, okay.